Okay, so to round out our study of the renal system and our study of the kidney, we've been thinking about balance. We thought about balance of water. Last time we were thinking about balance of sodium because we need to keep our salt concentrations constant. So between those two topics, we talked significantly about ADH, so our antidiuretic hormone, primarily its role here in controlling water reabsorption. And then we talked about aldosterone. So aldosterone coming from our adrenal glands, but kind of the end product of this RAS system, our renin, angiotensin, aldosterone system, which in the immediate term affects our salt reabsorption, so our sodium reabsorption, but then has downstream effects on water balance as well, because once we have a lot of sodium in our blood, we then in turn have a trigger for ADH release, driving water reabsorption after as well. Okay, so we had our overall effect of aldosterone as immediately we are increasing our sodium reabsorption, and then ultimately we are going to see an increase in blood volume and water reabsorption as we have that ADH kick in as a kind of secondary effect. So when we think about stimuli that start us down this path, start us down going towards releasing a bunch of aldosterone, we have to look at the beginning of this pathway. So we're looking for renin and its release from those juxtaglomerular cells. And our stimuli for the release of renin are going to be things largely that tell us that we have a kind of low blood volume situation, since our final effect is going to be to raise blood volume and raise mean arterial pressure. So the two things that directly relate to that are our first and last bullet points, really. So renin is going to be released when we see decreased pressure in the afferent arteriole. So that's the one coming into the glomerulus. So if we have low pressure in that afferent arteriole, it really means we have low blood pressure, basically, including in this arteriole. So this might be a time when we want to kickstart a bunch of water reabsorption, beginning here by releasing renin, making aldosterone, and doing some sodium reabsorption. This last piece is still related to that low pressure, low volume signal, but in a kind of funny way. So we are able to sample the filtrate coming up through the distal tubule through contact with these juxtaglomerular cells. And our signal for low blood volume, low blood pressure here is going to be a decrease in sodium and chloride ions in that distal filtrate. Now, we did mention that aldosterone, our end piece of this RAS system, increases sodium reabsorption, right? So you want to remember that it's not doing this really because we're releasing too much sodium. Our signal here is low sodium in that filtrate. But the reason there is the way you end up with this low sodium flowing through these distal parts of our nephron is that you have low flow overall, basically. So this shows us that we don't have a lot of fluid, we don't have a lot of quick movement here. And that's kind of a way we sense that. We also have sympathetic nerves that go to the kidney and can directly kind of cause the release of renin. Okay. So this is going in conjunction with a response overall to low blood pressure here, right? So we already know that the baroreceptor reflex, we know from our cardiovascular system, is a way we can get blood pressure back up, primarily by increasing resistance throughout the body, so kind of clamping down on our arterioles. Right? And now we're adding on these other kind of side pieces, right? So low mean arterial pressure creates this low afferent arterial pressure, which is a signal for renin release, right? In addition to that sympathetic activity helping us release renin. And then this low mean arterial pressure also means we're going to see a low glomerular filtration rate. And if you don't have low pressure, you're going to have low pressure of the blood in those glomerular capillaries. So you're not going to get as much plasma filtering into the nephron, which means that not as much sodium and chloride are coming in either, which means not so much sodium and chloride in those distal tubules, which is a signal for our cells in this juxtaglomerular complex to release their own signal for renin release. Okay, so that's aldosterone. Okay. Now we have one other hormone that acts on our sodium reabsorption here. Okay, so A&P is our atrial natriuretic peptide here. So this is why the heart actually is a secondary endocrine organ. Remember, the primary endocrine organs were like glands that their main job is to secrete hormones, but we had secondary endocrine organs that also make hormones. This is one of the heart hormones. So this is coming from the atria of the heart when we have a distended atrial wall. So we're seeing the blood returning to the heart, kind of ballooning that right atrium out, right? This is our signal for A&P release. Okay. So overall in this situation, right, this basically means we have a lot of blood volume, a lot of blood flow. So we're going to see that we have increases in glomerular filtration rate. We're going to see dilation of our afferent arterial, constriction of the efferent arterial, and our overall goal is to decrease our sodium reabsorption. So we mentioned that sodium reabsorption is happening because we have sodium channels in the apical membrane of our distal tubule cells, as well as cells in the collecting duct. And then we had our sodium potassium pumps, like always, on the basolateral membrane. And we can control how many sodium channels we have on that apical part. Nothing we're going to do about the pumps. So A&P, when it's present, is going to decrease how many of those sodium channels are open. And our overall effect is we're going to pee out a bunch of sodium, right? So we are going to leave a bunch of that sodium in our filtrate that's going to your bladder as urine. Okay. So here's what a flow chart for that looks like, right? So our overall kind of stimulus for this is an increase in plasma volume. So lots of extra blood, basically. Right? And this puts pressure on your heart, right? There's kind of, I don't want to call it a war between your heart and kidneys, right? But when we're balancing the plasma, you want to have enough blood pressure to send out blood to all your organs. But at the same time, like if you have too much plasma volume, that's going to put stress on your heart. So when we have this atrial wall stretch, we're going to protect ourselves by releasing A&P here. So A&P heads to the kidneys, right? So it's going to increase our glomerular filtration rate here, right? So ultimately that means more fluid is going to each of the nephrons, more fluid is going into the kidneys, which means ultimately you could potentially pee more fluid out, right? But you're definitely going to get rid of extra sodium. Okay? And the kidneys at the same time are going to cut out secreting so much renin, which means we're going to cut out aldosterone. So we're going to not be reabsorbing sodium into the body. Overall, we're just trying to get rid of it. Okay. So that's our sodium stuff, right? So big picture here for sodium is know that aldosterone increases sodium reabsorption, so keep more sodium in the body. A&P does the opposite, right? It stops our sodium reabsorption. And then our little final note is on potassium. Potassium balance is going to look basically the same as sodium balance, but just the reverse, because our sodium potassium pump takes things in opposite directions, takes sodium and potassium, I should say, in opposite directions. So we're going to be watching this flow in opposite directions. Okay. So hyperkalemia is, oh, am I not sharing my screen? I am not. That's going to be annoying. Okay. But I gave you guys backup videos as well in our recent announcement. Okay. Okay. So hyperkalemia, all right. We can see that K in the middle means you have high plasma potassium. So hyper for high. Hypokalemia means you have low plasma potassium. And this is bad because, again, our excitable cells, which are neurons, muscles, including the heart muscle, are expecting certain concentrations of things like sodium and potassium in order to have all those electrical forces, all our gradients pointing the right direction so that we can send off action potentials. So we need to keep our potassium levels in balance, just like we need to keep sodium levels in balance. Okay. All right. So if we're tracking potassium through a kidney, we're going to head through our blood vessels to the capillaries of the glomerulus. At that point, potassium is freely filtered into the nephron, nothing blocking it. In the proximal tubules, we do see potassium reabsorption. And we're going to travel through the loop of Henle. We know that we do some pumping of solutes in order to adjust our medullary osmotic gradient. But by the time we get to our distal tubules and collecting ducts, we're going to do some more reabsorption of potassium, but also potentially some secretion here. So that secretion piece is the bit that we're going to focus in on when we think about what additional facts do we want to know about potassium. So we're going to see that reabsorption, that secretion, I should say, in the distal tubules and the collecting ducts is regulated. So it's responding to hormones. And it's responding to a familiar hormone, actually. So it's responding to aldosterone. So aldosterone is regulating that secretion. Okay. So in terms of triggers for aldosterone, one of our other triggers for aldosterone release just is directly potassium in the plasma. And so the more potassium you see in the plasma, the more aldosterone you're going to expect to be released. They don't know all that much about every single ion and how it works exactly. So you'll notice unknown mechanism is here on our diagram for how potassium gets reabsorbed in the proximal tubule. But we do know more about what's going on in the principal cells in the late distal tubule and the collecting duct, right? So here we can see what's happening, right? So when we see secretion, we know that that means that we're somewhere other than the glomerulus and we've got something going into our tubular fluid, right? So we can see that ultimately that's the direction for potassium here, secretion. And we can see that this is going to be dependent on our sodium potassium pump, right? Which is creating a high potassium gradient inside our principal cell, which means we've now got a high to low potassium gradient so that through facilitated diffusion, so this passive transport, we can move potassium into that tubular fluid on the way to the bladder. Okay. So this is coming from aldosterone, the signal, just like it affects sodium, it also affects potassium, right? So when we have aldosterone in our bloodstream, we've got receptors inside our cells that can sense that. So these are cytosolic receptors. So aldosterone can actually get into these cells pretty easily, right? It's a steroid hormone that doesn't actually need much help getting into cells. Okay, so we got a receptor for aldosterone. And what it does is it increases how much we're pumping both sodium and potassium, because we do them together, on that basolateral membrane. So that's number one. So that's going to make those sodium and potassium gradients stronger that we then release when we open channels. All right, so more of these pumps. And then we open up potassium pumps at the same time as opening up sodium pumps. Okay. So those are just channels. So the only thing that can happen through them is passive transport. So the only direction those ions can go is along with their gradient. Our potassium gradient, you just mentioned, high to low towards the tubular fluid. So that's our secretion. And the sodium gradient, right? Sodium is being pumped out here on the basolateral membrane, which means we had a low sodium region here inside our cell. So our sodium, when it follows its gradient, goes in, right? So that's how sodium is being reabsorbed, but potassium is being secreted from this same signal, from aldosterone. Okay. So that closes us out for the things we want to know. I do highly recommend for all this hormone stuff that we covered at the end. Gave you a bunch of different tables, but I think this one is probably particularly helpful, at least from my view, for kind of abbreviating what you want to key in on when you're thinking about hormones related to the kidneys. So we've got our two effects of aldosterone on here. So when you're filling out those blank tables, you're going to write what hormone. You're going to be thinking about what substance we're regulating in the distal tubule and collecting duct. You want to know what direction that substance is going in reaction to the hormone. We got a little mechanism piece here. And then a bunch of these are also going to relate to blood pressure. So we've got an effect on the plasma directly, and then an overall effect on mean arterial pressure and blood pressure. Okay, so we got aldosterone, A&P, which we just briefly mentioned, coming from the heart, and ADH, our friend regulating water reabsorption. Okay. So that's what we got for final content on the kidneys for today. So we can return to review time. So that's one of the printouts, was a blank form of this that I had for you up here. I believe the other ones, we had one on parts of the nephron and what they do. And what was the third one? Oh, our Starling's forces. So looking at that glomerular filtration rate. Other things you can do is be going through the practice exam and asking me questions about that, or you can feel free to go get started on your Easter break.